Hello Abaqus users! Hope you're doing well. In this workshop, we are going to simulate and analyze the 3D printing of a gear by a stereolithography method. See this model? It is a simple gear, and the final result should be like this after we are done with the simulation. You see how the layers are peeling up and forming the gear. This contour plot animation shows the temperature changes with a scale factor of 20. To do this simulation, we are going to use Python scripting and subroutine. Now let's find out how we should proceed to have a 3D printing simulation like this. First thing first, we need to model the gear. You can see its dimensions here in the top view. By now, you might have this in your mind. I saw the layers are peeling up in the animation, so I need to model each layer. That's not quite right. First, you must model the gear in the Abaqus or any CAD software and layering your model in some pieces. For example, we layered this gear into 5 pieces or layers, and the thickness of each is 2 millimeters. This isometric view is for just one layer. After that, we use Python code to import the layers in the Abaqus. We use Python scripting for simplicity's sake, and we will explain more later. Look at these two figures. We can layer the model in 2 shapes: discontinuous and continuous. In the discontinuous shape, we have some discontinuity here or here. But in the continuous model, we have neat and uniform layers. This model is simpler and we will face fewer problems during the simulation. Moreover, our Python code supports only the continuous shape. Next, we need to specify a point with fixed x and z coordinates and different y coordinate, for example, from this area. This point must exist in each layer, and we call it the reference point. The meaning of this point is different from what we called in Abaqus CAE as reference point. You can see the coordinate of this reference point here. In each layer, only the y component of the point will differ. Just be careful when you pick the reference point, because it shouldn't be picked from the edges or free space. It has to be on a surface. Another difference between the discontinuous and continuous layers is you can pick a reference point in the continuous model but not in the discontinuous model. We need this point in the Python code. We will explain more in Python scripting. Now let's define the material properties. First, the mechanical properties. Density equals 1120 kilograms per cubic meter. The expansion coefficient equals to 0.000124 per Kelvin. And the elasticity will be calculated by the USDFLD subroutine, because in the 3D printing with the stereolithography method, the elasticity is not constant and will change during the process. If you remember, we said that the 3D printing method we chose is stereolithography. In this method, a liquid called resin will be polymerized with a laser beam and form the model. The energy of the laser must be enough to polymerize the resin. Take a look at this diagram. It has been obtained through an experiment on the resin XP 5081-1. For more details, refer to reference number 1. But let's see what it is telling us. The horizontal axis is logarithmic and indicates the energy of the laser. Its unit is millijoule per square centimeter. The vertical axis indicates the polymerization depth in the resin based on millimeters. This diagram wants to tell us how much energy the laser beam needs based on the resin properties to polymerize it in the desired depth. For example, suppose we need to polymerize the resin to the depth of 0.1 millimeters. In that case, the laser energy must be almost 10 millijoules per square centimeter. This point that intersects the horizontal axis determines the critical energy, or EC, which equals to 5.6 millijoules per square centimeter. If the laser energy is less than this amount, the resin remains liquid. If the laser energy equals the critical energy, the resin will not be completely polymerized and will have a jelly shape. But if the laser energy is greater than the critical energy, the resin will be completely polymerized. Now we understand laser energy and how it works. The effectiveness of the laser energy will decrease during the process because some amount of the laser energy will be absorbed by the resin. Therefore, we need to calculate the required energy in each layer with this equation. For more details about this matter, refer to reference number 1. En is the required energy we have been talking about all along. It is called the effective exposure of laser energy in the nth layer. E0 is the exposure energy at the surface of the resin. Z prime is the investigated depth in this layer. dP is the average penetration depth per layer, or as you see, it's the slope of the diagram. And D is the thickness of the layer. After we calculated the required laser energy, we will use it to calculate the elasticity during the process. When the model is created, the resin will change from a liquid state to a solid state by the laser beam, so we will have the temperature changes. Therefore, the elasticity module will change as well. Look at this diagram. You can see the elastic module amount and its behavior in different temperatures. By now, you might have figured it out that elasticity is a function of laser energy and time. Therefore, the elasticity module will be calculated with this equation. For more details, refer to reference number 2. Y is the elastic modulus. Y max is the maximum elastic modulus. Beta and alpha are the dimensional constants calculated from the tensile test. E is the laser energy that we calculated by the previous equation. EC is the critical energy of the laser. All of these variables values will be inserted in the USDFLD subroutine, so you will see their values there. Next, we need to define the thermal properties. We have conductivity, which is temperature dependent, latent heat, and specific heat, which is also temperature dependent. You can see the values in these tables. Now let's see what the boundary conditions are. Look at this picture. This is a schematic of 3D printing with the stereolithography method. The stereolithography method is done in two ways: bottom-up printing and top-down printing. Here we use bottom-up printing. The bottom-up means that the laser or projector will emit upward from the bottom of the machine. You can see all of the machine components here. When the first layer is created, it will stick to the bottom of the platform until the end of the process, so we need to apply that in boundary conditions. Moreover, when a layer is being created, it is in the tank and won't be able to move in the vertical direction because it is tangent with the bottom of the tank, like you see here. After it's created, the platform will move upward as much as the thickness of one layer, and the next layer will be made. Let's see what happens during the simulation to better understand this matter. First, you need to know that this simulation will be done in 6 steps. Only one layer will be created in each step and its boundary condition will change. In the first step, the first layer is created. The top surface of this layer will be constrained in the U2 direction, because if you remember, from the previous slide, the surface of the current layer is supposed to be tangent to the bottom of the tank and won't be able to move in the vertical direction, which is U2. So we must apply this condition to be like reality. This condition will be deactivated in the next step because the platform needs to move vertically, so the next layer will be made. Therefore, we need to deactivate the constraint. The bottom of the first layer must be fixed from the initial step to the end of the simulation, because like we said before, it sticks the bottom of the platform. The second layer will be created in step number 2. As you see, the U2 direction is no longer constrained in the first layer. So the second layer must be constrained in the U2 direction for the same reason before and will be deactivated in the next step. As we said before, the bottom of the model is fixed. Next, the third layer is created in step 3 and the top surface of this layer will be constrained in the U2 direction and will deactivate in the next step. You can see that the 2 layers before are no longer constrained in U2 direction. In the next step, the fourth layer is created. Like before, the top surface is constrained in the U2 direction and will deactivate in the next step. Again, the bottom of the model is still fixed. The final layer is created in step 5. Like before, the top surface must be constrained in the U2 direction during the creation of the layer and will deactivate in the next step, and the bottom is still fixed. In the 6th step, the top surface of the 5th layer is unconstrained and no other layer will be made. In this step, the cooling process will be completed. And of course, the bottom is fixed. In summary, each layer must be created in its own step and be constrained in the U2 direction only in its own step, and the constraint will deactivate in the next step. And the bottom of the model must be fixed in the entire simulation. Another boundary condition is temperature changes. In 3D printing with the stereolithography method, we have temperature changes due to laser emitting and the liquid resin turns solid. At first, the temperature of the layers is high and in time it will decrease. We will calculate the temperature changes by the DISP subroutine. Look at this diagram. It wants to tell us when each layer is created. It has T max temperature at first. In time, the temperature will decrease linearly to reach the T0 temperature at the end of the analysis. In other words, the temperature of each layer is high when it's created and it will cool down in time. We assume the temperature changes of the layers are linear. For example, the temperature of the first layer will start to decrease linearly after it's created, and the equation of this line would be like this. By this equation, you can find the temperature at any time in this layer. The temperature changes of the second layer will be like this and start after the layer is created, and its equation is this one. As you see, the temperature changes of the other layers start when they are created. The general equation of temperature changes of any layer is this one. I is the layer number, Tp is the time period, and N is the total number of layers. T max is the initial temperature of each layer, which equals 80 degrees Celsius. T0 is the temperature that the layer must cool down to reach this temperature and equals 25 degrees Celsius. This term of the equation calculates the slope of the line. To obtain each line's slope and whole equation, you just need to insert the layer number instead of I. See the equation of the first 2 layers, for example. In summary, the temperature of all layers when they're created is 80 degrees Celsius and will decrease during the simulation to reach a temperature of 25 degrees Celsius at the end of the analysis. Just remember this linear equation is just our assumption, and you can calculate the temperature changes with your own equation. Until now, we have discussed initial conditions, material properties, and all things we needed to know to understand what we are trying to do. But let's organize our thoughts to know better which steps we should take first to do a solid simulation. Look at this flowchart. The first thing we must do is model the gear in a CAD software or in the Abaqus itself. Next, we should layer the model in the way we have talked about. We can do this with the same CAD software that we modeled the gear or with the Abaqus. Or you can combine these two steps and model just one layer in any software you prefer. Anyway, in the end, you need to save only one layer of the model with the extension .igs or .sat in a folder with the specific directory. Our next move should be preparing the Python code. You might ask yourself now, why do I need a Python code? How is that going to help me? Do you remember when we talked about the boundary conditions and steps? If you want to define them one by one in the GUI, it could take some time and would be exhausting. Yes, it is just 6 steps and several boundary conditions, but this is just a tutorial. In reality, you might have hundreds of layers. What about then? Moreover, there are some other things you need to do for the simulation, which we will tell you later, and it's easier to use Python scripting. Long story short, it would be easier and better to use Python scripting. You will be better understand later. Next, we must import the layers file we have saved to the Abaqus. You can import it directly into the software, or you can import it through the Python code. But as we said before, it's better to use Python code and import the layers file directory to the code. After that, we must prepare the USDFLD and DISP subroutine. Finally, we just run the Python code and wait till our job is completed. Hello everybody, and welcome to our new video training package of Abaqus. Additive manufacturing simulation with Abaqus subroutine and Python, 3D printing Python. This package includes these sections: Lesson, Introduction to Additive Manufacturing. Workshop 1, 3D printing Abaqus simulation of gear with DISP, USDFLD and Python scripting. Same cross-section. Workshop 2, 3D printing Abaqus simulation of shaft with DISP, USDFLD and Python scripting. Non-uniform section. Thank you for taking the time to watch this video. We hope it will be useful for you.